So I'm going to talk about Artemis regions from a solar illumination perspective. And this is in a Shackleton session, but actually it's a little bit broader than that. And so I'll get through those. So the first thing I wanted to say is that even though maybe it's known to some, I think it's maybe not pervasively known or at least appreciated, is that the typical illumination conditions at the, that are typical for the equator regions are very rare at the poles. And so this is why this is such a challenge and needs to be thought about and accounted for in all aspects of the mission planning for Artemis. This shows a map of a shaded relief of Lola, and on top of that, you see in red the average illumination between 25 and 50%. So 50% is what's in deep red, and so you see that's quite limited. If I narrow the sort of range to 40 to 60%, you can see those regions are extremely rare. And so looking at the statistics of that, you can see here a plot versus latitude of how much of the surface is at the 50% or greater average illumination. And you can see it's pretty constant throughout, between 60 and 90 at about 1%. And the reason for that is that to get even just 50%, you need to be pretty clear of any obstacles around you. The polar regions are obviously very interesting because they get some of those higher average illumination locations. You can see the 60% line in yellow, which is basically completely zero up to 85, and that's where some of the region becomes highly valuable in terms of solar power. If I zoom out now back to the 100% level, right, the whole surface, you can see that really what the issue with the overall regional conditions is that the moderate illumination regions, at 40% or above, are the ones that really have this strong decrease as you get closer to the pole. Where the majority of the region is like that at let's say 60 degrees latitude, and it's again quite rare at the 85, in the Artemis region, 84 to 90. So I just wanted to put this out there because it really makes should make us appreciate that those regions that were selected host some of those pretty rare, very special places that can enable exploration of the South Polar region. So I'm going to discuss some different metrics that are linked to illumination, and so those are obviously the average illumination that I just showed a little bit, but also key for both operation on the surface and design and use of assets on the ground. An important metric is the maximum darkness period, which happens during the winter season, and so those can be thought of as constraining or sizing your sort of battery or your energy system. And then also the maximum sunlit period, which have implication for what was just discussed a few minutes ago in terms of flexibility, in terms of launch dates or landing dates, or even exploration sorties around a site. And I'm going to show different simulations here that were done at 3 different heights. At the surface, which is obviously important for both, for example, terrain relative navigation, but also just astronauts on the ground being able to see what they're doing. At 2 meters, which is sort of a low altitude, low elevation sort of placement for solar panels of maybe the first systems that will be deployed or that are deployed at every mission. Also looking a little bit at midterm needs, right? Explorability of the surroundings, how far you can go from the site, connecting between neighboring regions that are especially present, closer to the pole. And also I've done some simulation at 25 meters, which is probably a little further along, but could be thought about as long-term exploration assets that obviously would have more favorable illumination conditions and then provide more capability once you establish maybe a long-term presence. So the first one is the average sun visibility. Here I'm showing the 13 sites, and I should mention also that those simulations were made again recently based on the 20 meter per pixel LoRa map that Mike Barker presented yesterday. And so I should also say that we hope to be able to release those soon, and all the different maps you'll see, we'll try to make a package for that at some point. And so those simulations were done at the surface over the whole lunar precession cycles of 18.6 years. And you can see some of the regions. All of them have some of those very beneficial high illumination region. So this is for the whole 18 years. If we just look at the summer season, you can see that, especially, for example, the Connecting Ridge, which is well known, peak near Shackleton here, especially the Malapert region, and the Gerlach Rim and the Leibniz Beta Plateau all have favorable locations for summer season exploration. If you look at the equinox, this is actually much closer to the average map, not surprisingly. And so those still have, it's hard to see, but some red pixels that are at the 70% level in a few places, but you're much more restricted. And in the winter season, very few locations are actually good. And so that's why the winter season, I think, is going to be challenging in the near term for actual, crewed missions. And the game, if you want long-term assets, will be to survive that season. So here are the histograms of those maps. And so starting from the winter at this point, you can see why the winter season is so challenging. The best location are sort of at the 50-60% level, meaning that the nights are going to be pretty long. The equinox, and then here the summer solstice. So I added an inset here showing a little bit the situation at 90% and above. And so hard to place those right now, but those are the regions that have especially interesting locations for the summer season. Another thing that was published actually a couple of years ago in the paper that Mike Barker published about the 5 meter per pixel DM, those were used to look at the longest darkness periods. And so that was done here at 2 meters altitude. And so you can see this is the Connecting Ridge region. And you can see there are a few areas that are pretty small, a few hundred meters, that have longest darkness period in the winter of just a few days. And so those would be sort of minimum duration you would want to size your battery, for example, to have multi-year assets on the ground. And so this was at 2 meters. And so recently we did that at 25 meters. You can see that region grows significantly. The longest darkness period goes down below 2 days, actually. And so you can imagine that, longer term, more assets, more mission could take advantage of that zone. Obviously, being careful about self-shadowing between the different elements. But this becomes a more sizable area to work with once you have panel technology that can go higher altitude. So this had been done for just a couple of regions in the past, and recently I did that for all of the 13 sites. And so here the color scale, a bit hard to see, but has been up to 15 days of darkness in the winter. So everything that's red is basically, not a very different system that you would need to do for the equatorial region at best, right? So you probably want to stay on those rims and those high terrain. And you can see that some of those regions actually do not have really interesting winter places to hole up and survive. And so you can see that about half of them, 9 of them have some of those regions. But as you can see from the previous slides, those are actually pretty small as well. So those are very special places that you may be able to take advantage in at some of those regions. Now the histogram of that, this is the number of pixels of 20 by 20 meter pixels. So it's very few locations at the 2 meter level. And so this will be more interesting at the 25 meter level again, because this is where you get a lot more area and more sites are again potentially good, right? The Connecting Ridge here stands out as the best with the shortest winter nights. But some of the other ones may be also in the sort of 5 to 7 day range, which is still a lot better than planning for 15 days of darkness. Okay. And so here are the maps now of the longest sunlit periods at 2 meters. And so the idea here is that if you want to do a mission that may have a little bit of flexibility in terms of landing, going to a location which is just going to be sunlit for 6.5 days, or I think which is one of the sort of minimums you would want. That's going to be difficult because if it gets dark afterwards, right, the plans need to change. And so there are a few places here. The color scale goes from 0 days of sunlit period, which is a PSR, to 100 days in the summer. And so you can see there's some locations have at least 100 days of continuous sunlight at the 2 meter level. in many of those regions, not all of them. Again, there's a few that do not have that. And so those could be helpful to, as sort of targets so that you have more flexibility in your schedule for landing. And so again, here in terms of histogram, the connecting ridge is the one that has the longest ones. Actually, this one, even at the very low altitude, you can get summer days of above 200 Earth days. So that gives you, a lot of flexibility. Obviously, those areas are pretty small, but you can imagine that around that area, you can probably move around a little bit to share some of that. And then, Leibniz Beta Plateau and Malamute Massif are always, in that category of 180 to 200 days. So now, if you look at 25 meters, basically Connecting Ridge gets an extra month and goes to 260. And Nobile Rim 1 also goes, sort of in the top tier with Leibniz, Beta, and Malapert. So
1 minute.
Yeah, thank you. Yeah, so here I'm going to skip, the Earth visibility, as you know, is mostly connected to whether you're close to the near side or not. So Nobile Rim, for example, here is interesting, but Leibniz and Malapert are very good in terms of Earth visibility. Most of the other regions are really just average, with the Earth only half visible through half of the month. So may require some, assets in orbit. The one thing I want to say is that I've also looked at mobility, how mobility could help you explore the region around the landing site and also connect different regions. And so here, this is just, looking at the connecting ridge. If you could travel for up to 100-kilometer round trip and you needed the surface to be fully sunlit for 5 full days, this is sort of how far you could go. And the color here indicates how many days per year you could start your trip. So this is just a heat map sort of what are the most accessible locations with those constraints. Obviously, constraints can be changed, but this is the idea. And last, I'm just going to show something that we did recently, a study that we did about connecting different regions, Artemis regions, through probably a robotic asset at this point, but that could go between missions, crewed missions, to bring assets or something. And so here the goal was to show that some trips exist that never go into darkness, and so could relieve some design requirements on the rover, for example. And so this was published. If you have questions, I can give more details.
All right. Thank you, Erwan.